Section 4.7, Graphing Motion. This is a little run through of some of the different things that can go on when you're graphing motion and interpreting the motion of an object by looking at the graph that represents its motion. And there's two types of graph you would generally see. One would be position on the vertical axis versus time on the horizontal axis. The other one would be velocity versus time. So if we start with position, which is measured in meters, and on the other axis, time, which we normally measure in seconds. Time is always going to be on the horizontal axis, no matter what. If I plot some data, let's say like so, I have a series of points and they all run like that. I can draw a line through those points right now, and let's suppose that this is 1 second, 2 seconds, 3 seconds, and so on, and this is 1 meter, 2 meters, 3 meters, and so on. Then, if you think about calculating the speed or the velocity, it's just distance divided by time. And if we look at the graph, if we want to calculate the average speed, say between t equals 1 and t equals 3 seconds, then I'm going to measure the time as this distance on the graph from 1 to 3, and I'm going to measure the speed, d, off the vertical axis. So there's d and there's t. So looking at the graph, my speed is basically the rise over the run, or it's equal to the slope of the graph. So that's our first major piece of information. The slope of a position versus time graph is giving us the speed or velocity of the object. So I'm just going to clear up my graph and move on. So in one color I might draw a straight line that represents the motion of one object. Pick another color, the motion of a different object. If you look carefully at the graph, the blue object has traveled further than the orange object in the same amount of time. If I read position versus time, the slope of the blue graph is steeper than that of the orange graph. It's telling me that the blue line represents the motion of an object that's moving faster because the slope of the graph is steeper. These two graphs, a blue line there, an orange line here, they have the same slope, so they represent two different objects traveling at the same speed. But they start at different times. So this is two objects traveling at the same speed, but starting at different times. I can draw in a third line, the red line, now compared to the blue line. Again, the slopes are the same, so they're traveling at the same speed. They both start at t equals 0, but the red one is starting from a different position, further up that axis than the blue one. So these two, the red and the blue, start from the same place at different times. Sorry, they start at the same, from different places at the same time. My mistake, sorry. Different places at the same time, and these two start from the same place at different times. Just look at that for a little bit and satisfy yourself that you can follow that. The other thing I can sometimes put, you will often see on the vertical axis instead of position, is velocity, and that has units of meters per second. And that gives us some different information. If I plot now something that's changing by the same amount every second, if there's 1 second, 2 seconds, 3, 4, and if I make the velocity 10 meters per second, 20 meters per second, 30, 40, then again I've got a line that goes through these points. And if you remember that acceleration is defined as change in velocity divided by the time, then for this example, let's look at the time interval between 1 and 4 seconds. So the time interval, delta t, is the run, and the change in velocity, delta v, is the rise. So again, acceleration on this graph is the rise over the run, which is the slope of the graph. And some of you might have noticed the values that I've picked here. In this case, my delta v goes from 10 to 40, so the change is 30 meters per second. And the time interval goes from 1 to 4, it's 3 seconds. And so I'm ending up with an acceleration of 10 meters per second, or 10 meters per second squared. So this is actually a graph of velocity versus time for a free-falling object with an acceleration that's acceleration due to gravity. But generally speaking, the slope of a velocity versus time graph is going to give you the acceleration of the object. Another really useful piece of information that a velocity time graph can give you is actually the distance traveled. Let's imagine an object that moves at a constant velocity. This is v equals 30 meters per second. You can read it off the graph on the left. And it travels at that speed for a total period of 5 seconds. Well, we know that the average velocity, which in this case is the same as the velocity it's traveling at all the time, is d over t. So the distance traveled is v times t. Distance equals speed times time. But if we look at the graph, the speed is this distance on the graph, read off the graph. And the time is this distance. So when I multiply speed by time, I'm actually calculating the area of this rectangle here. And it turns out that even if you're not moving at a constant speed, the area under that curve is still, under that line, is still going to give you the distance you've traveled. I'm going to clean this up and show you a different example. Now let's suppose that the velocity is all over the place. It's changing all the time. We can get any shape we like. If I look at a small section of it, like between these two times, what is it, about 1 1/4 seconds and 2 seconds down here, then this shape is almost a rectangle. Its speed for that short little amount of time is about the same. So I could, if I wanted to, work out the area of that little rectangle, and then I could work out the area of the little rectangle next to it the same way, and I could just keep on going until I've worked out the entire area under the curve, and that would still tell me how far this object has traveled. To do that properly requires calculus, which is way beyond the scope of this course, but you can estimate that just by counting the squares under the graph. So for example, if I wanted to figure out how far it had gone between 0 and 1 second, I want to figure out the area that I'm just enclosing in red now. Well, I can just count the squares as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That and that and that. Partial squares there add up to maybe 11 squares. So maybe it's 11 squares. Each square is half a second by 5 meters per second. And so it's 11 times 5 is 55 times a half roughly 23 meters. Just by counting the squares and recognizing that each square is not one, but you've got to count how many meters per second along the edge it is and how many seconds it is along the other edge. So you've just got to keep an eye out for that, but you can estimate the distance you've traveled just by the area under the graph. Finally, I'm just going to go back to a position versus time graph, this time for a free-falling object. And if you apply d equals 1/2 gt squared to calculate the distances that the falling object will travel for each of these times, 1, 2, 3, 4, 5 seconds, you should find after 1 second it's about 5 meters, 2 seconds is 20, 3 seconds is 45, 4 seconds 80 meters, and 5 seconds comes out to be 125. So we end up with a graph that looks like that you should recognize, having seen it several times now. And then if I just fit a line through it, you'll see that it's a curve, getting ever and ever steeper. So the speed at any given time is the slope of the line at any particular time. So if I pick that point there, the slope of the line, the slope of the red curve at that point is approximately the slope of this black line that I just drew. At this point here, the slope is kind of like that. At this point here, it's getting steeper. So the slope of the line of a curve at any particular point is giving you the speed. And you can see in this case it's getting faster and faster as the curve gets steeper and steeper. And you look at the equation that we use to calculate those distances. D is equal to something times t squared. That makes this curve a parabola. So if the acceleration is constant, the position versus time graph is going to be getting steeper and steeper, and it's going to be a parabolic curve, distance proportional to t squared.